this is Mr. Ward, and I'm going to demonstrate how we can use scientific notation to make some really extraordinarily complex calculations very simple. So I'm going to look at a little thing called Coulomb's law. This is a thing that shows up in physics and chemistry and a lot of scientific concepts. Coulomb's law has to do with how much electromagnetic force there is between two objects that have electrical charge. And here's the formula. F stands for force. K is some number. It happens to be 9 billion. And Q1 means the charge, the electromagnetic charge of one object. And Q2 is the electromagnetic charge of another object. And R squared, that's the distance between the centers of the two objects. Let me go ahead and consider two objects. So we're going to consider a proton and electron. Now, first, I have given us the mass of a proton and the mass of an electron, but we're going to consider them by charges. In a few minutes, I'm going to walk us through the force of gravity between them as well. So we're going to consider an electron and a proton that are 1,000 meters apart. That's 1 kilometer. Okay, this measurement R is a distance in meters. So here is how we set up the equation. K is going to be this 9 billion number, but I'm going to write it as 9 times 10 to the ninth power. So I'm going to say 9 times 10 to the ninth power. Then the charge of an electron is -1. So -1. The charge of a proton is +1. So 1. And then I'm going to divide that all by, I'll do this here, divide that all by 1,000 meters, which is 1 times 10 to the third meters. And I'm going to raise that to the second power because I've got to square this. Okay, so I've got all of that information. Okay. And we get a negative number. Here you can see Desmos has already calculated it for us. This is really not that hard to organize, though, on our own. What we do is we separate the coefficients, the 9, the -1, and the 1, and the 1. So that becomes 9 times -1 times 1, all divided by 1. And that's our coefficients, which is really easy. That's just -9. Then we deal with our powers, which is 10 to the ninth. And then I'm going to go ahead and take us through the powers. This is times 10 to the 0. That's times 10 to the 0, so I don't really care about that. But I am dividing by 10 to the third to the second. So that's going to be minus, since it's dividing, 3 times 2. Okay, because when I raise a power to a power, I multiply the powers. When I divide a power by a power, if they're the same bases, I subtract. So I end up with 9 minus 3 times 2, which becomes 9 minus 6, which becomes 10 to the third power. And so 10 to the third power is 1,000. And that's where we get -9 times 1,000, which becomes -9,000. Or -9 times 10 to the third power. So -9 times 10 to the third power. So the electromagnetic force between one electron and one proton that are 1 kilometer apart it's negative. That means they're attracted to each other. That's why that negative is there. But it is 9,000 newtons, 9 times 10 to the third newtons of force between them. And if we wanted to find out what that was in pounds, we divide that whole thing by 4.45. Okay, and we get 2,022 pounds of force attracting an electron and a proton towards each other. That's a lot of force. Now let's consider instead of electromagnetism, let's see how much gravitational pull they have between each other. So this becomes 2 times 10 to the third power, basically. Negative, of course. So I'll put that in there. Now, gravity is also going to be attractive. The equation doesn't end up creating a negative, but we're going to need the mass of these two objects. So this is the equation for gravity. The force of gravity is going to be 6.667 times 10 to the negative 11th. And then we're going to multiply that times the mass of one object times the mass of the other object. Okay, so the mass of one object is this. That's the mass of a proton. And we'll multiply that times the mass of an electron. There. And I'm going to stretch this out so you can see the whole thing that's happening here. And then we're going to divide that by 1 kilometer, but we're going to have to square that. So I'm going to raise that to the second power. So 1 times 10 to the third power. Okay, you can already see that's a really tiny amount of gravitational pull between that electron and that proton. Okay, so we're going to do what we've been doing to do operations on scientific notation. I'm going to separate the coefficient operations from the power operations. So I've got my coefficients are 6.667 and then times 1.67. So times 1.67 and then times 9.1. That's the coefficient for the electron. 1.67 was the coefficient for a proton. And then that's all divided by 1 cubed, or 1 squared, I mean. So let me just do this. Don't really need to do the division by 1, but I'm just going to go ahead and put it in here for coherence of structure. So I get a coefficient that becomes 101.3. Now I'm going to separately deal with the powers. I'll come back to that in a second. I'm going to separately deal with the powers. I get 10 to the, and I'm going to put this in parentheses, negative 11, because this is multiplied, 10 to the negative 11th times 10 to the negative 27th times 10 to the negative 31st. I'm going to add all of those powers. So plus negative 27 plus negative 31. And then I'm going to subtract the power in the denominator, which is 10 to the third to the second. So I'm going to say minus 3 times 2, because I need to multiply those since it's a power raised to a power. I can do all of this because it's all the same base. 10 is the base in all of these cases. Okay, let me go back. I'm not sure why it moved around like that, but there we go. We get 10 to the negative 11 times negative 11 plus negative 27 plus negative 31 minus 3 times 2. I'll go ahead and take care of the 3 times 2. That's a 6. And then we'll deal with negative 11 and negative 27. That's going to become negative 38. And then plus negative 31 will become negative 69. And that minus 6 is going to be negative 75. And so we get a 10 to the negative 75 power. I don't need the parentheses anymore. And we put it all together, and we get this number, 101.32 times 10 to the negative 75th. Now, I want to make this scientific notation, so I need to make this 100 times smaller. That means I move the decimal 2 places. So I'm going to put it there. And if I made that 100 times smaller, I need to make this 100 times bigger by going from negative 75 to negative 73, going up 2 orders of magnitude. So now we know how many newtons of gravitational force there are between this electron and this proton that are 1 kilometer apart. Okay, Now, how much bigger is so? Which one win? Which one wins? Electromagnetism clearly wins because we've got 2 times the 10 to the third, 2,000 newtons of attractive force. With gravity, we've got about 1 times 10 to the negative 73rd newtons of. I'm sorry. Let me back up because I'm mixing up units. So when we were dealing with just newtons, it was 9 times 10 to the third newtons of force versus roughly 1 times 10 to the negative 73rd newtons of force for the electron and the proton, okay, for gravitational force. So it's a whole lot more massive, a whole lot more incredible force, electromagnetism, compared to gravity. Gravity's hella weak, don't you think? So um, later on, maybe I'll do a video on what if we had a kilogram of protons and a kilogram of electrons? What would the gravitational force be between them? And what would the electromagnetism be? I'm going to go ahead and stop now. I hope that was helpful in seeing how you could organize all of those pieces.